Okay. Probably not. I think it'll detract from the screen. I want to shut my own cell phone off. I'm presenting, yeah. Yeah, I'm presenting data still. Do you want to go ahead and put them up on the... Okay. And then I'll start as soon as you're done. Yep. Finish putting the schedule up. And then... Don't know if we ever were. Correct. Oh, yes. What is it? HBO Productions or something is his. Yeah. I don't know whatever happened with that. We were working with him, and then I think he dropped the project or something. So. Well, let's talk about it after. Nice, Bruce. Okay, why don't we start? Good afternoon, everyone. My name's Joe Pulea. I'm going to be talking to you today about the Mars Homestead Project, a project of the nonprofit Mars Foundation. It is quite literally a project, the intent of which is to design, fund, build, and operate the first permanent settlement on Mars. And, you know, we really think that we can open a new frontier here. And our mantra is to arrive, survive, and thrive. I think that encapsulates everything we're trying to do here. So here's an outline of what I'm going to talk to you about. Initial destination Mars. Why do we think that that's the place to go? How do we get from this vision that we're going to present to you today to reality, to actually establishing this settlement? And I'm going to go through some of the details of what our vision is. Compare some of the resources that we have to work with on Mars and compare them to circumstances and situations here on Earth. Talk about the resources that are available on Mars that we can use to build a new home. And then we're going to talk about how you guys can get involved in helping to make this happen. So we think that Mars settlement is the definitive element that is going to open up the solar system to humanity. If you look at the other locations in the solar system, whoa. Is there some in between? Yeah. Okay, anyway. If you look at the other locations in the solar system where we could establish a permanent settlement, well, let's examine them. Earth orbit. That's not a great place to put a permanent settlement because there's nothing there we can utilize. On the moon, well, there's all kinds of extremes, and there's certain resources that the moon is lacking. It's lacking water, it's lacking nitrogen, it's lacking carbon, and we feel that all of those elements are plentiful on Mars and easily accessible. Asteroids, you've got lots of concentrations of resources, but no one location that has everything that you need for self-sufficiency. And self-sufficiency is the key. Because if you want a sustainable settlement, you need to focus on self-sufficiency. And I'm going to talk more about that. So this is where we decided to put our focus. Now, this is not to say that we're anti-moon or we're anti-asteroid development. On the contrary, we want to work with groups that are interested in going to these different locations because we think that there are technologies that are common, there are systems that we can work on together, and eventually there will be the establishment of an inner solar system economy with trade, resources going into different locations. And if you really want to talk about self-sufficiency, you have to have some trade in there. Because there are certain things that are going to be better produced in some locations, but are scarce in other areas. Okay, so how do we get from vision to reality? Well, we started out by going through something we call programming. It was, in essence, a feasibility study where we pulled into the team groups of experts in different fields. And we tried to come up with technical concepts for the settlement and integrate those concepts together. And so this was an iterative process. We went through 3 different phases. And I'm going to talk to you a little bit more about that. Then, so that's just completed, and we're going to be presenting today an awful lot of the material that we've developed over the course of this 8-month programming study. What's going to happen now? Well, we're going to do prototype projects. There's a lot of elements of this that we can break down and have sized such that a small group, a university group, a bunch of enthusiasts can get together and really accomplish something of value. So I'm going to talk about that some. And then Research and Outreach Center. We feel that what is really needed is a central location where we can pull together all of the elements of the Mars settlement and serve both an outreach function to spread the message of Mars settlement and also perform some of the research that needs to be done in order to get us from here to there. And eventually, the first privately funded Mars mission and the establishment of the actual settlement. And I'm thinking there are probably quite a few steps in between here, but one thing at a time. So challenges of Mars settlement. I love this picture. It really does seem like that's the wall we're trying to climb. But it's not all that difficult. We can break the problem up into chunks that we can solve. We're going to have to focus on flexibility, not mass production. So if we can send one piece of equipment that can do 10 different things, that's ideal. Worker productivity is going to be very important on Mars. We're not going to have a huge labor pool to draw from. So every worker is going to have to be as productive as they can, and he's going to have to be skilled in multiple things. Earth-Mars transport, obviously, is the limiting factor. And so we're going to try to focus on manufacturing high-mass elements on the surface of Mars as opposed to importing them. And this gets back into the sustainability element as well. If we're constantly relying on importing large amounts of material from Earth, it's just not very sustainable. Let's see. High-tech items, though, can be typically low mass. Sensors, computer chips, complex mechanisms. A lot of these things we'll import. Mars unknowns, dragons, sea serpents, savages. There are things that there are going to be surprises. There's going to be things that surprise us when we go to Mars. And so we need to be prepared to deal with that. And then let's move on. So here is our vision of the first permanent settlement on Mars. Now this is sized for approximately 12 people with easy expansion beyond that. And it's built primarily from local materials. In fact, we're aiming towards, now this is not for the initial settlement, but once it's built, we want to be about 90% self-sufficient by mass, self-sufficient. And we want to put in place the industrial capabilities that will allow us to continue to build, to repair things that break, and to expand. And we chose this as our focus, this initial settlement, because once you have this initial toehold in this new world, and you have this industrial capability, we feel that once you accomplish that, the rest is kind of, okay, I could see that we could expand beyond and keep going. But this is the defining factor. So we picked a site on Mars just to give us a little bit better context. We selected a location in Valles Marineris. It's actually in a side offshoot of Valles Marineris called Candor Chasm. And this is the location. Zooming in, so you can see here's a context picture, and then there's some high-resolution swaths through here. Continuing to zoom in. And we're not really set to this location. This settlement could be put in different locations than this. But we wanted to pick some site so that we had a context and we could really get a feel for what it might look like. Now, this particular site that we chose, there were some criteria that we had to select. One was we wanted some big flat areas where we could land different cargo elements and crew. And you can see the settlement is going to be right here. Okay, anyway. So what happens? What's the progression for building this settlement? The first thing is we're going to land tuna can habs. We call them temporary construction trailers. They're going to be very much like the Mars Direct or NASA Design Reference Mission habs, and they're something that our construction crew can live in while they're setting up the industrial processes, while they're setting up the water and the power generation, and they're pumping out the materials that they can use to build the settlement. So here is a plot of our settlement concept. You can see that what we do is we dig into the side of a hill, dig away the loose material, and then we build inside the hill here, right at the base of the hill, we build masonry structures, vaults and domes, and then we cover them with regolith. And the regolith provides both shielding from radiation and also it counterbalances the pressure forces. And then when we extend out into the plane with these large greenhouse modules, with other modules, we need tensile strength structures because there is not enough soil overburden to contain the pressure. So you can see we've got your main entry here. The next slides go into more detail, but we've got lab space, we've got lots of public spaces and open green areas, private suites looking out across the Martian plain, greenhouses to support the crew of 12. And then this is the real meat and potatoes. This is where the industrial processes are, the manufacturing, the mining, the refining, the gas plant, gas storage. So we chose to design using standard modules because there's a limit to the number and variety of modules that we can produce with any set piece of equipment. And so this is the modules we chose. These modules, longer modules for the greenhouses, manufacturing. Here's a cross-section of our settlement. Now this particular cross-section shows some vaults and domes, and then leading out to the edge of the hill where there's less regolith, you see we have tensile strength structures. It either could be spun fiberglass, it could be metal cylinders, it could be some kind of bladder that holds the pressure. And this is a very important characteristic of our settlement. It's the first tree. It's symbolic of bringing life to the new frontier, to the new planet. And we're not sure exactly what kind of tree it would be, but it's a dedicated space for that. Zooming in, here's a little bit more detail. You can see here's the suit room, EVA prep, some mechanical shop areas. Here's a rover garage and a rover-sized airlock, so we can bring it in and work on it in a shirt-sleeve environment. The greenhouse areas, and I'll show you more details in a sec. Greenhouse support, waste treatment. Here's the private suites again. Now you can either have these modules double wide, in which case it could be for a couple, or we can partition them and have individual suites. Large common area with a dining area and a kitchen and a bamboo forest and water culture surrounding it. Labs, medical area. And that was the first floor, and then as you move up the hillside, there'll be another layer of these private suites. The common areas will be 2 stories, so this will be nice and have some volume to it. So don't think of a cramped tuna can hab. The idea is that people are going to go here and they're going to live a significant portion of their lives here. So it needs to be someplace where you or I would not mind going and living and not go crazy in living in these tiny spaces. And this is hot off the presses. This is an artistic rendering we had done looking out these windows across the Martian plain. And you can see each personal space would have an area set aside for some greenery. So in essence, you're looking through the screen of greenery out on the Martian plain. Zooming into the other portion of the settlement, you can see we have 2 large manufacturing areas where we manufacture all manner of things, and I'm going to go into details. Some airlocks for getting products in and out. Power for the base is provided by nuclear reactors, and a lot of people see this and they say, why do you put the nuclear reactors so close to the settlement? We need to put it miles away, put it behind a hill. The truth of the matter is that you can get very adequate shielding with some water and with regolith. And you can reduce the radiation levels down to the same as the background radiation level. And also, think about this. There are, I don't know how many, but there are quite a few research reactors on the campuses of major universities in the United States, right next door to dorms. So, this can be done safely. And another reason for putting it right close to the base is that we want to integrate the reactors with our manufacturing processes. We want to make use of the thermal energy that they can provide. And I'll show you in my nuclear and electrical talk that it's a significant usage. It's a definite advantage to have them there. So here's our concept again. So I talked a little bit about how we can expand beyond this. So this would be the initial settlement. It would be for 12 people. Set up the initial infrastructure, the initial habitable space, and then what we call build phase 1. And then we could expand. We could continue to use the infrastructure and the mining, refining, and manufacturing processes that we have put in place to continue to expand, to provide redundant systems, additional redundant systems, to provide additional living quarters, and to expand the population. And so this could eventually continue all the way around this butte. You could burrow into the hill and make connecting tunnels and passages. We think it's a kind of nice concept. So this is what we're aiming for. We want to extend human civilization to the red planet and have people that are born there, that live their lives there, they work, they have fun, they get married. So here's a little bit of a comparison between, this is probably preaching to the choir here, but comparing Mars and Earth. I'm not going to go through all the details. I'm sure you're pretty familiar with it. It is more extreme. It is going to be a difficult environment, but it's an environment that we can overcome, we can work with, we can engineer solutions to these problems. So I talk about building this great settlement. How do we do it? What resources do we use? Well, we're going to bring some things from Earth. We're going to bring the equipment we need. We're going to bring a lot of the initial infrastructure, the metal manufacturing process, the chemical plant, some initial tanks, some bulldozers and trucks, and the nuclear reactors for power. So there's quite a few things that we're going to bring from Earth. But we're trying to leverage use of the local resources, because doing that, one, it helps us move towards self-sufficiency, and two, it lowers the entry to barrier, or the barrier to entry here. So, obviously, if we can produce 100 tons of materials that we need to build the settlement there on the surface, we don't need to import that from Earth. And also, we're going to have to focus on how can we get humans and robots working together well. And this is especially important considering that there are not going to be all that many people on Mars. And if you look at all the things that we need to do to build this settlement, I'm not so sure that we can have a guy there with a trowel and bricks, laying a brick wall. We need to automate some of these things, and we're looking very closely at these issues. Okay, so here's some more detail on the resources we bring from Earth. For the entire settlement, constructing the entire settlement and getting it up and running, we need 250 metric tons. Now, compare this to 3 round-trip missions of, say, Mars Direct or NASA Design Reference mission. This is comparable. This is very comparable. How do we get away with that? We get away with that because we remove what you need to come back to Earth. Now, we may want to provide some capability for that because you need ticker tape parades. You need to bring back some heroes. But if you think about the settlement of this country, was it settled by people that came over, spent a year doing science, and then went back to Europe? No, it was colonized by people who came here, they sold everything they had, pulled up their roots, and they came to the New World because they saw the opportunity, they saw the potential. And we want to have that same kind of situation here. So if you replace everything that you need to bring home with settlement cargo, you can get away with a permanent settlement on Mars for the same cost as 3 Design Reference mission or Mars Direct missions. I talked about labor. We're going to have very highly skilled people, cross-trained in many disciplines. We're going to provide them temporary living quarters and life support, a lot of dry food to get them through until their agriculture gets going. Power systems, we're going to send nuclear reactors. This is something that we can do. And I'll talk a little bit more about that in my nuclear and electrical talk. Electrical distribution components, construction equipment, a lot of the things we need to set up mining, refining, manufacturing. These are the kind of things that we're going to make on Mars. We'll produce gases by splitting water and by sucking in the Martian atmosphere. We're going to produce all different kinds of chemicals, metals, plastics, ceramics, masonry, glass. These are turn of last century or even prior industrial processes. This is not rocket science. We know how to do these things here on Earth. And the idea is that these things, which are relatively low tech, turn out to be the highest mass items that we need to produce. So they're ideal for initial industry on Mars. Robots and animation systems we're going to bring. Also things that we scavenge from the landing craft. I can just see us running around pulling wire and batteries and maybe even turning some rocket engines into smelters and other things. There's a lot that can be done there. So I talked a little bit about the Martian atmosphere. We're going to be sucking in the CO2, and it's actually there's nitrogen and argon in the atmosphere, so we're going to be producing buffer gases, condensing that out and producing buffer gases for our habitat. And also the CO2 is important. We can use compressed CO2 for cleaning off spacesuits, for various compressed CO2 tools. And we have a whole other talk about how we're utilizing the atmosphere and what the gas plant criteria is. Okay, so here's some more of the details, what the composition is. The products, we're going to obviously produce oxygen, the buffer gases, methane, so that we can have internal combustion engines running around and run our construction equipment and various different things. Longer chain hydrocarbons leading to plastics. And Frank is going to give a presentation a little bit later about the details of the plastics manufacturing system. Martian water. We feel that, we really hope that the Mars Express orbiter finds a subsurface aquifer somewhere close to the equator, because that's where we're putting the settlement. If you look at settlement of this world, it's followed the water. Every settlement that's done really well has had a good source of clean water, drinking water available. And we think the same thing is going to happen on Mars. We're going to go where the water is. Greenhouse water use. So I don't have numbers on this, but we're going to have, it's not going to be a completely closed system. If you talk about settlement of space in general, people are really focused on getting 99.99% closure in their systems. That's not required for Mars. We don't need to spend years working on 100% closed life support systems. The reason is because we have the resources of the planet to work from. We're going to have some leakage of gases from the habitat. Okay, we've got the equipment there that we can replenish those gases. We need more water. We can tap that aquifer and we can get more water. I love this image. This is just great. This is a concept of our of our transparent greenhouse. We actually have two different kinds of greenhouses. We're hedging our bets here. One is a transparent or a translucent greenhouse. So we grow plants using the natural Martian sunlight. And some plants will do great with that, and other plants need more light than that. We'll also have another set of greenhouses that are artificially lit. And you'll see in my electrical talk that the electrical load is significant, but we can do it. We can get by. Martian soil. So this is another resource that we have to use. Turns out there's everything in the Martian soil that we need for industry. All the essential minerals and elements are there. Ooh, that didn't turn out too well. There we go. So just to show you, I mean, this is the overview presentation. So this is giving you a high-level view of our concept and what we've been doing. But we have dug very deep into the details. This is just one slide that gives you a feeling for the detailed level for our ore beneficiation processes. And I'm not going to go through it all with you, but I just wanted to give you a flavor. We need your help, guys. We need your help to make this happen. Now, we fully support the government's Moon Mars program. We think that there's a lot of opportunities for funding some of the settlement development work, technology development work, off of that initiative. But we need to work now to develop these systems for permanent settlement so that when the transportation elements come online, we're ready to go. We're ready to push the button. And we need your help to do this. So building beyond the programming effort, the initial feasibility study, we've established a series of task forces to concentrate on areas that we didn't have a lot of time to focus on in the initial study. We have a group that's working, it's actually a group of students at the University of Central Florida and at University of Illinois that are working on a mission plant concept for delivering our settlement cargo to Mars. We've got another group down, a civil engineering group down at University of Central Florida that's working on a large module task force. So what are these structures that we're building? What's the cross-section? What is all the different elements that goes into it? Site selection, obviously, is going to be something that's going to continue to be refined as more data comes in. I mean, that's the kind of thing that we can spend a whole year just studying what's the best site to go to. It's not necessarily required, mind you. But we do want to look and find a site that has a good mixture of available resources and has the water that we can tap. Vehicle task force, so we're looking at some of the robotics, the automation, the different vehicles we're going to need. Polymer synthesis, Frank is continuing to work on that and has made great strides. And spacesuit task force. This is actually my brother generated this rendering of Mars skin suit. I'm sure many of you are familiar with the concept. So we've got some people that are looking into spacesuit design. This is kind of cool. So I talked about how you guys can get involved. Well, one thing is you can join one of our task forces, and we're always looking for more people to help us work on these different things. And also, you can work on prototype projects. Now, there's all kinds of things that can be done. It could be something as simple as figuring out, let's see, what some recipes are that we could make different meals on Mars. Or it could be making a tabletop process demo. Or outfitting a single module and getting a feel for space layout. There's a lot that can be done here. The Full-Scale Research and Outreach Center, we're making great strides right now towards establishing this center. We think it's very important. It's our next main project. And the idea, again, is to combine both research and outreach. So to build somewhere here on Earth a full-scale version of this Mars settlement that you and I can walk through and really get a feeling and realize this is not rocket science. This is not something way out science fiction, way outside my level of understanding. It's just a home. It's a home that happens to be on Mars. And this center will also allow the visitors, allow the public to interface with the researchers that are working on making this happen. So we're very excited about this, and stay tuned. That's all I have to say. So with that, this is the Mars Homestead Project. Thank you for your attention. You can see some of the folks that have been working on this and the different areas that they focused on. And I'll be giving a talk in a little bit about electrical and nuclear systems. So, you could live here. Help us make this happen. Any questions?
Let's only take general questions. We go into a lot more details throughout the afternoon.
Any questions? Yes.
The site selections that you're, just the general view, Gus Frederick was talking about using lava tubes.
Mm-hmm.
And obviously that would be huge in terms of the amount of earth that would have to not be moved and so forth and so on and so forth. So is your site selection flexible enough to allow you to utilize that kind over a huge resource?
Certainly we could if, one, you could tell me where a suitable lava tube was located, and if, two, you could confirm that it was structurally sound and stable, or that we could shore it up and make it stable. These are unknowns right now, and so we didn't want to lock our concept in on using a lava tube and assuming that there's a great lava tube waiting for us to discover. Yes, we could certainly locate nearby. Now, our particular settlement concept calls for a building into the hillside. So hopefully the lava tube is going to be located someplace close to a nice hill that we can build into. But we are flexible. Seems like a nice hill to build into. Any other questions? Yes? Do you remember what the exact date was? That 2025 for this settlement to be built and come online. Now, you might say, oh, well, you guys are just throwing a dart. That date is based on a detailed schedule that we have developed that incorporates the development time necessary for coming up with these systems, for engineering these systems. And also, it's looking at, in parallel, the development of the capability to deliver these systems to the Martian surface. So we feel that there's going to be a convergence. Hopefully there will be a convergence. And we will be able to establish this and get it up and running in 2025.
Actually, 2025 is the answer we gave the IRS. That's why I remember it.
Any other questions? Well, Bruce, shall we move on to the Bruce McKenzie? Another co-founder of our group is going to talk to you about the architectural concept for the Mars Homestead Project. He'll talk about it in more detail. Our architect, Georgi Petrov, couldn't be here with us today, but Bruce is going to fill in.
So yeah, I wanted to introduce Georgi Petrov, but his boss decided to grant him in Russia. So it's on a business trip to the
You want the microphone, Bruce?
Notice I put the schedule up for the afternoon. It is as is in the program. There have been no changes for today's program, except that where you see a name in parentheses, it's presented by the person in parentheses. I'm on a leash, and you can hear every word I say. Does this just go in my pocket? Okay, so let's see. I had wanted to introduce the people in the room, but anyway, we've been working at this hard for about a year, and it's based on some of the preliminary stuff that I and Georgi Petrov and several other people, some of whom are in the room, have done earlier. We're trying to pull it together. But anyway, you just met Joe Pelea. Georgi Petrov was the architect. I'm presenting it. I'm Bruce McKenzie. Next, waste processing by Gary. Joe will come back for the electrical. Joe is presenting Damon's work on the gas processing. Frank Crossman on polymers and plastics. Joe presenting Damon's work on metals. And then discussions on what projects you or a Mars Society chapter might want to do that fits in with this or has some connection. And then discussion about raising the first families on Mars, what would be like to have the first kids. Then you're welcome to hang around after that here, and then we're going to move over to the club level and just kind of have a get-together for anybody who wants to chat casually. If there's someone local who knows of a pizza place we can order out, we'll do that. Tomorrow, unscheduled, Manju is going to be talking about the information processing. That's not in the schedule. So, Georgy Petrov was born in Eastern Europe and emigrated as a child to this country. He worked as a civil engineer and then went back to school at MIT, got a Master's of Architecture. And I was on his kind of thesis, it was called a reading committee. I was one of his thesis advisors. He incorporated some of my masonry work and a lot of other work into the presentation, into his thesis work, and then we pulled a lot of this together as the Bars Homestead project. Mark Homnick, Joe Palea, and other members of the Homestead team contributed. By the way, this is Gary Fisher, and Frank Crossman is over there. There's a good 6 or more people on the team here at the conference. Okay, a little background. This paper was presented by Georgy at the ICES conference. It's an environmental, space and environmental conference that was over in Rome, Italy about a month ago. And I'm using his view graphs. Somebody made classifications of different ways to settle planets. You could bring everything pre-assembled from Earth. That was considered kind of a class 1 settlement. Class 2 settlement is the Design Reference Mission or the Mars Direct Mission, where you bring stuff from Earth, but you do some assembly. And maybe you use a little bit of local resources, like for propellant. What we're talking about in this project is phase 1 of permanent settlement, or class 3, where you actually build a fair bit from local materials. ISRU is in situ resource utilization, and you bring some stuff from Earth. As you just heard, our initial base is designed for 12 people, but it would grow by 12 every year, up to about 100. At that point, you might branch out and start outlying settlements. Who just came in and was not here for the past half hour? Oh, good. Okay. Yeah. All right. So I will give brief summaries of what's going on.
If you move it down, it's too close to your.
No, I can't stand further away from my chest. So, okay. Oh, from the laptop. Okay. Sure. Okay. So. Like all good architects and engineers, Georgy looked at what are the requirements and the environment that he had to design for. Gravity is lower. There's been some debate as to whether you're going to hit the ceiling as you walk, going up the stairs, things like that. Temperature is much lower. The ambient temperature is down around -60, -40 centigrade. It gets up to around 0 centigrade once in a while. Even though it's cold, it's not necessarily chilly. So if you leave a tool out overnight, that tool will be -60°C. But if you go out in a suit and you're exercising, the air is so thin that it won't cool you very fast. So sometimes you have to you have both cold and warm problems. And then you obviously have to wear a pressure suit. Air pressure, I think everybody knows this. The red shows the top of the Olympus Mons is about 1 millibar. That's 1/10 of 1% of Earth pressure. Hellas Basin is the lowest. That's still 1% of Earth pressure. As an architect, Georgy had to expect radiation and provide for it, shielding from the solar wind, cosmic rays, etc. And the biggest requirement is just being a long way from home, a long way from help. So. Okay, 2 basic construction methods. One is you have a pressure vessel, something strong that will hold the tension, against the internal air pressure, and either inflatable or a rigid shell. Again, we want to make all this on site. Another method that really is only usable on Mars is you build a masonry structure, it basically vaults, and you put enough dirt on top of it that it holds the air down. The pressure of the dirt goes down. I had presented previous work at past conferences on this, but Georgy really developed this quite nicely. And they can be arches, vaults, they can be leaning masonry where you stack the masonry inward. And comparing the two, if you have a membrane that is in tension holding the pressure, it's fairly easy to have. You can have lots of small spaces. You can have windows, nice views. You only need to cover it with 1 meter of regolith or so for radiation protection. This is the method that you would use where you have a door to the outside, where you want to be very close to an exterior door. Compared to using regolith, you have to pile so much dirt on masonry. You have to pile so much regolith or dirt on top of the masonry that that dirt will spread out, and it's really only good for interior spaces, far away from a doorway. And we're proposing about 10 meters of regolith. You can get by with a little less, depending on the density and safety margins. But assume 10 meters of regolith, which is an awful lot. And there's a trade-off between the cost of the tensile material and the effort of moving the regolith. You have to make sure that the load lines, that the lines of force are inside the masonry vault. If I wasn't on a leash, I'd go over and draw it. But basically, picture a vault, and the force of the regolith going down through the masonry has to stay inside the masonry, both when it's pressurized and unpressurized. Hopefully, robots, teleoperations would do most of the construction, and people would only be used for the fine detail, or where a robot can't handle a construction, maybe at a corner or a door frame or something like that. By the way, in the lower left, number 4 and number 5, one of those is Yorgi, building a small vault out at MDRS. Was anybody here who's seen it? Yeah, good.
It's still there.
Yep. Yep. By the way, I have a previous presentation where I collect pictures from all over the earth of masonry structures, and some of them are like from Pompeii. There's a 25-meter wide arch over in Iraq or Iran. So, ideally, construction would be done under some kind of construction tent where possible, some kind of temporary inflatable. Might be pressurized with CO2. We are assuming that we would manufacture standard size pressurized membrane, inflatable I'm sorry, many of these would be rigid, but standard size modules. I'm leaving masonry, going on to the tensile structures. And some of them are pretty long. You see the greenhouse there is, down the lower right, it's 33 meters long, a third of a football field, and we're putting 2 of them end to end. So you could have a quite